return. We look at investments on the basis of risk and return, two items. And we'll look at this the same way, in fact, we'll look at a two-dimensional model, but pretty similar. Any entity's multi-criteria score will be the same as the other scores if any efficient entity's weighted score is going to be the same as the other efficient entities, that each efficient instructor is going to have a score of 1. These entities are called efficient DMUs. Okay, table 2. Okay, so there we go. So I basically went through that massive data. We have 20 instructors and 8 criteria, and I basically said, let's just look at the top 8, that is the first 8 on the list, instructors, and only at the impartiality criteria and the preparedness criteria. Note that OBA, I just made up, these are randomly assigned initials, OBA had a very good score as far as being impartial. The students really thought this person was impartial. Wasn't particularly well prepared, but better prepared than a lot of others for class. And the average, simple average, would be a 4.28 for that instructor. On the other hand, if we use a weighting scheme of 3.33 and 0.7 for the weights, we'd see that person had a value of 4.08. If we basically look at all the others, we see that the top performer as far as simple average is OBA, yet when we have something that has a weighting, importance weighting of twice as much or more than twice as much for being prepared versus being impartial, which may or may not be a valid weighting scheme, we see that the top performer is actually OLK. And the OBA drops down. So the ranks are very sensitive, oftentimes, to the weight schemes, the importance amounts you apply to the criteria. Graphically, we can see OBA, OLK, and OBB on this frontier. Basically, we draw from the extreme point in the vertical dimension, which is impartiality. We draw a horizontal line back to the axis, and it provides a hull, part of the hull that's basically going to serve essentially as a concave hull that OLK and OBB are on, because OBB drawn to the vertical horizontal axis, and we see the hull shown there, and then basically essentially on this set of people who are on the outside of the group, those are clearly the best performers. Is one of these better than the others? We're not trying to address that. We're at this point with DEA. All we're trying to do is find out from set of data which ones are on the frontier there, which performers are on the frontier, and then on top of that, once we find out people who are inside, we basically take a look to see which peer group, that is, which best performer or efficient performer is closest, and therefore which one might be serve as a good mentor or something of that nature. So the graphical view of the data is on the previous slide.
John, could you go back 2 slides?
Yeah.
It doesn't appear to be, looking at the ranking, whether it's simple average or weighted average, not much more than one difference.
That in this case, there's only a slight difference.
Is that generally the case? Or?
Sometimes it can be a very severe difference, but generally those who do well in the simple average are in the top half of the simple average. They're going to be in the top half, regardless of the weighting scheme you use. Yes. Again, it depends upon the data. And for this set of data, it's relatively minimal.
And you said the data was randomly generated.
Yeah, these are data randomly generated.
So that's pretty.
Yeah, I've been wanting to find some time to actually put real faculty evaluation numbers in there and see how it works. But it's a lot of time involved that I haven't gotten to. This is a paper I've been working on for a long time.
So statistically, is there a significant difference here?
Since we're not dealing with sampling, it's a sampling process. It's not the concept of significance doesn't really have a true meaning at that point. So we'd have to talk in terms of some other measures, such as a substantiality measure and so on. So, and the answer to that is, I don't know. I have not decided to come up with any particular measures to say this is a significant or substantial difference and this is not. I have not looked at any research to say, what should be considered substantial? 10% changing places, or a change in rank of more than 2, or there are some.
But it's possible to play with those ways to produce major differences and outcomes.
Yeah.
Now, that's true.
Yeah, for
But is it-
example.
but
Is that basically what you're asking?
No. I'm asking you, is it worth it? In other words, to go through this effort versus what we're using, when the rankings aren't changing. None of the one ranking looked like changed, stayed the same, number 4. And all the others changed maybe 1. So there's not much change in the ranking. Then-
Well, there could be, depending upon the chair's sort of subjective assessment of the importance of these various criteria.
But maybe that's what ought to be looked at, is the subjectivity of the individual who's looking at it. Maybe that ought to be narrowed down more specifically, so that from chair to chair, it's not a subjective matter, but rather based upon concrete criteria. That's where I'm getting at. That, plus the fact how much difference is there between number 1 and number 2. We're talking $50 or $75.
That's what I was about to say, yeah. Basically, using real data, looking at real raise information could have some bearing on.
Could take you from an A to an A+.
That's right.
Well, what are the weights based on right now? You just randomly.
These I just said, let's just try,
Okay.
what might be,
No,
anything I want. For example, I said, well, suppose impartiality is considered much more important, 4 times as important as fairness. Well, then we see something that shows that 1, 3, and 2 are the same. Ranks 1, 2, and 2 are the same essentially for the efficient performers, as it turns out, OVA, OVB, and OLK.
actually,
But anyway, the other ranks change a little bit. I just wanted to do that to address the concept that weights can make a difference.
well, I think that I see one aspect of Ralph's question is in terms of significance. What you can do, what can be done is if you do a conditional systematic simulation of going, say, from 1%, 99% weight to reverse 99 and 1. You could simulate that using crystal ball or something, and then see where those points converge at. And if there's if it's all in a ball, like all the points, the millions of points that you'll get in one ball, then there is not too much of a significant difference. But if it's all spread out, then there is a possibility that weights really matter. And I think that's what you're getting at, right?
Yeah, well, I think Chris
Statistical significance is not, I think, possible to really calculate from this. It is one way.
It's basically a guessing game. In other words, what I'm saying, it would be nice is if, as a faculty member, we could look at the criterion, and we could come up with, within a number or two, of exactly the same number that the evaluator or the department chair in this case comes up with. And in many cases, I'm sure that it's off by 10 or 15 points because of the subjective factor. And if that's the case, is any system going to be?
Well, that's why weighting is a flawed system. Nobody really can agree. And by the way, I didn't have it on here, but that's something to add to this thing of where to go from here. That future directions, whatever you want to call it, is do some simulation on this and to address the concept of simulation. Okay, some basic definitions. Efficiency is going to be defined specifically for our purposes as output over input. Maximum possible efficiency is constrained to be 100%. That's, you can't get any more out than you put in, at least through our definitions we're working from here. Output for an instructor is his or her average evaluation score, so we're defining that as the average, the output for an instructor. Input for all instructors is theoretically the same. Basically, you've got this time, you're basically using 100% of that time. We're not addressing how well you use your time. We're basically looking at the output. So it's essentially an output model. DEA can be defined as an input-output model, or it can be defined as an output model, or it can be defined as an input model, depending on how we want to approach it. We're looking at the DEA output model. So, again, we can look at what we have as far as data, and then recall how I modeled the lifeless number problem, and basically say that what we're trying to do at this point is choose the set of criterion weights for a given instructor. So just pick any instructor. Choose it, try to find a set of criterion weights that will maximize, make that instructor look as good as possible. Subject to, when those weights are applied to the other instructors, that the output over input is no more than 1, or moving on down. Since our input is defined to be 1, so that the weighted average score is no more than 1 for any instructor for a given set of weights, for that set of weights. The instructor's weighted average score is maximized, as large as possible, and we keep the weight values positive. Since each instructor's input is defined to be 1, that's why we go from the input-output model, the general model, to the pure output model here. You basically simply replace one input with 1, realize that output is just weighted average, and we basically get what we have, an essentially defined model. And we'll look at the numbers in just a second, the actual model and that stuff. By doing this, we have defined the weighted average as something scaled between 0 and 1. So that's a little caution. So you don't go thinking that the output, the weighted average that results, is something you can compare to directly the initial weighted average. Okay, let's let W1 and W2 be our decision variables. We had X1, X2, X3 in the Leibniz limit model. Then, for instructor GJB, just what I picked at random, we're trying to maximize 3.02 W1 plus 2.83 W2, subject to basically the other instructor's weighted average scores being less than or equal to 1. Find weights such that the weighted average scores for the other instructors as well as this one is no more than 1. You use Excel to model this, but we need to reformulate and solve for every instructor. So we have to do this for every instructor. So we basically go through this. For every instructor, which is a pain if you have the rest, you write it out and didn't have some macro to help you out with this. And basically figure out which ones come up with a value of weighted average equal to 1. Those are the efficient instructors. Let's see. That's where macro programming comes in. For our basic model, once again, related to Leibniz number. Here we have the green showing the decision variables, and then the yellow showing the coefficient values for the constraints and the objective function. We have the constraints shown as the available, the results of applying a set of values for decision variables in this column, and something fairly similar here for the set of instructors. We have our objective function, which is to maximize 3.02 times whatever weight we choose for the partiality, plus 2.83 times whatever weight we choose for preparedness. Let's see, do I have the model tools? Solver. Yeah. So I basically built this information into Solver. I said, take this value right here, maximize it by changing these values, subject to these values being no more than these values. Pretty much parallel to the Leibniz number problem. And that says for GJB, the best combination of weights is 0.05 and 0.2. We're not really concerned about those, but we see that the best GJB can ever do is a 0.7 on efficiency. The GJB is not efficient. Oh, wait, go to slide. GJB is right here. We could have pretty much told that by plotting it. We can't do that if we have large, more than 2 dimensions. I did it in 2 dimensions just so we have a correlation between what we see here and the results. But the nice thing about the approach we've taken is we don't need to solve the graph. Keep those values. But again, this is a pain because now I have to, for the next one, I have to take OBAs, 4.77 and 3.78. In fact, let me just do that once. And if I had a macro button, it'd be a little faster, but I will do that in the next screen. So I copy and paste, and I see, okay, OBA is efficient. Now I have to write that down on another piece of paper. That's a pain also. So not only do I have to copy and paste and resolve, write it down on a piece of paper.
So that the algorithm is not selecting the weights that would make an individual faculty member's score as high as it could be, subject to the constraint that the sum of the weights has to be equal to 1. What the algorithm is doing is selecting the weights that will make the combined scores of the group as high as it can be. Is that right?
Actually, you're right the first time. It says, find these weights right here that will make this one look as good as possible, but as long as we apply those same weights to everyone else at the same time and keep those values below 1. So we're not actually...
But if we just solve the algorithm with the constraint for just the one, you see, faculty member, you see that the weights may come out different.
Oh, yes, definitely. Yeah, it could come out different because we're not worried about, in fact, it can come out to 1, be efficient, but we have to basically, the whole concept of efficiency is relative to the others in the data set. Okay, I've just cleaned things, or enhanced things a little bit on this page. I added a column to indicate DMU number, and then if I put, for example, 1 in here, it will automatically I suppose automatically update those values. Let's see here. Well, anyway, I'm not sure why it's not doing that, but basically, if I put 1 in here, oh, yeah, it does. Okay. If I put 1 in here, I wrote this and I don't even remember myself. Put 1 there. It basically says, okay, this is item 1, so we put OVA stuff in there. If it's 2, it puts DAV stuff in. So I basically, if I just click on Run DEA, it basically is a very simple little macro. I'll show you in just a second before I say goodbye. It's a macro that basically just puts down 1 in here, then 2 in here, then 3 in here, then 4. And each time it puts something in there, it basically runs solver and puts a result up here in this column called efficiency. And so we see that OVA is efficient, OVB is efficient, OLK is efficient. Now, solver, no, I should leave the toolbar up. The macro has a few more lines. Instead of just solver, solve, user finish equal true, it says, okay, put this in a loop for unit equal 1 to 7. We can make this much more flexible. It can be based upon how many values there are in the data range. But and this is hard-coded 1 to 7. So basically it goes through this 7 times. And basically it sets in A12 a value of 1, which basically puts initially 1 puts OVA stuff in there, and then basically it puts 2 in there, and puts the next ones in there, and so on. Solves it, and then basically puts over in that efficiency column the result of the objective function value. Now, if we look at the entire set of data, this is just the QDL. We want to maximize this mess so we put this mess. That's a huge thing. We really wouldn't want to even put it in Excel if we didn't have to. But if we at least put the numbers in Excel, we don't have to go through over and over and over again and solve it. And basically the result is that OVA is efficient, Next was efficient, GJV turns out to be efficient when we consider the other criteria, and so on and so forth. Plus peer groups have been identified. Since we don't have time to go into identifying a peer group, I'll just simply say that that peer group is handy because it allows us to look at directions for improvement that are going to improve faculty, not just rate them. Now, when we compare the results of using data development analysis, we see those who are inefficient as these values who are, I should say, efficiency is the green line, reference line now. And those who are above the reference line are efficient. and those who are below the reference line are inefficient. So we see roughly half, a little less, about a third of the group is considered efficient, and we can see those who are inefficient. But interestingly, from this little graph, we can see who's more efficient, who's less efficient, even though the values of efficiency are defined to be 1. So we can then enhance this to come up with, oops, that's not what I wanted. We can enhance this to be more useful to our needs, being able to add constraints and things of that nature. That's where the word comes from. That is, we can constrain the weights. We can say, well, you've got to have at least a certain amount in this area, or this has to be at least twice as much as that, and so on. We can rank, we can do some stuff that ranks it basically among the efficient instructors, get some ranking there. And in fact, the techniques for doing this, there are several out there, and basically I proposed 1 or 2, and the work I've done actually discusses that further. You can span across the other criteria on the merit evaluation, so basically we've only looked at the teaching criterion. And note that there are some other applications that are actually for decision skill, or not addition. I'm not Indian. Indians say addition, right? Addition process. You probably don't know that. And you don't. But anyway, for decision support, basically, we've looked at evaluating results of parent decision. That's what DEA was developed for. But there's a neat area that DEA can be applied to as far as helping guide us with future decisions. And one of them I've got in mind is looking at different possible e-commerce platforms, web server, scripting language. John's been working on that sort of thing, and coming up with a structured approach to helping someone decide what's going to be best for that organization. Selecting vendors, I did a paper on using decision support, using DEA for vendor selection, comparing with other multi-criteria tools. And again, simulation and so on, as you already said.
Well, John, I have a question about the previous slide, but again, the efficiency parameters. Is it possible to adjust those parameters to get a Lake Wobegon effect, like where everybody's above average?
I won't go there, but as far as the slide, that would be interesting research to look at here. And basically, it could be considered a flaw of DEA if you could.
I thought that's one of the things about DEA.
Yeah. So I'm not. Yes, I vaguely recall something of that nature, but I'm glad you pointed that out. The Lake Wobegon effect.
Yes.
Significant step.
Everyone's above average.
How would you describe the end result? When you come up with the numbers, you come up with individual faculty, you use efficiency. What does that mean in terms of the merit system?
Yeah. Good question. What do we do with this stuff? Okay, we've got a handful of faculty, or 2 or 3 handful of faculty. What do we do with it? One approach might be to say all those who are considered efficient get top ratings on that particular area. For example, teaching, full points for teaching, or if you have to go across the whole scale, those people get the A ratings. Those who are inefficient may be gauged according to how far they are from efficiency.
I was following up on Chris's comment earlier. Are you saying with efficiency that person is the best by themselves, or that person is the best considering they produce the most good for the department considering everybody else? Then it is a measure.
Okay. It basically is not considering what the contribution is to the department. It does not consider the contribution and how well that person works and supports the mission of the others.
So it's really it's the same thing we're talking about now. Merit is just you have done X, Y, Z, which is the way the marketplace looks at people when you're moving from one job to another. They don't look at you and say, okay, now how well did you fit in the department? They look at you and say, John, what's your teaching research?
Yeah, it's basically a way of getting away from simple averages on set criteria, or getting away from using weights that people don't feel appropriate, but it still ends up the same thing. Yes, you are here, you get this much money, you get that much money. I won't address what I feel, what I
mean, if you just sort of randomly selected a faculty member and evaluated how they fared compared to the normal system, would it be the case that the items on the student evaluations where they perform stronger would tend to have higher weights than in the normal case, right?
Yes.
And those areas where they did not do as well would tend to have lower rates as a result of this optimization problem. Would that be the
Yes.
case?
It basically allows people to do what they do best without having to say up front how much I want to be evaluated on these sorts of areas.
Even though we do have different weights or different questions, but if you go through those questions, several of those questions actually point you to the same thing. So they're actually kind of.
Yeah, I have not got even come close to getting into the flaws we have with the questions we ask on our evaluation. Our evaluations are hideous. And yeah, we're asking the same thing several times, and oftentimes it boils down to, do you like this person or not? 35 ways of answering, do you like this person or not? So again, that's another issue that we are actually trying to take up with the planning committee and try to come up with something that's a little more appropriate.
If you were testing your model in terms of efficiency, and this may not be a good analogy, but in the marketplace of baseball and labor, you have employees that have been measured on a wide variety of output criteria. And you have salary numbers, and you have that data that goes back 100 years. Shouldn't I be able to take your model and plug in all the players and all those statistics and run it and come up with some kind of result that matches the way their salaries end up being the next year? But if it doesn't do that, then the model functions.
Baseball is a great place to do that, too, yeah, because they've got data that go back forever and lots of data and very good, very clean data. So yeah, that would be a very good way of doing anything that is testing multi-criteria analysis and decision-making approaches. That would be very good.
How do you account for the steroids and the greens?
We'll throw another variable in there. Thanks everybody for your patience. I appreciate you being here. Hope to have board